Hi, and welcome to RadOnc Talks, a lecture series designed for students and residents of radiation oncology. My name is Ria, and I am currently a PGY 5 resident at the University of Pittsburgh. Now, by no means am I an expert in medical physics, but I recently passed the physics board exam, and I spent a lot of time preparing for this exam and putting together some slides as my own personal notes. And since I'm working on this project of RadOnc Talks, I thought it might be a good idea to try and record some lecture style videos reviewing some very basic principles of radiation physics that all of us need to know as radiation oncologists, and hopefully this can even maybe serve as a review for folks that are preparing for the physics board exam. I'd like to kick it off then by talking about properties of photon beams, which is probably the most common type of radiation that we use in radiotherapy. Let's start by talking about what a photon is, how it's produced, and different types of photon interactions. The term photons refers to X-rays and gamma rays, which are both types of ionizing radiation that are on the high energy end of the electromagnetic spectrum. They're X-rays and gamma rays, and they are really massless packets of energy. So they have both wave-like and particle-like properties, but very importantly, they don't have any mass. Photons are the most commonly used modality compared to particle therapy, I would say. So we can also give radiation using particles such as electrons or protons, but photons are really the most commonly used when we think about diagnostic and therapeutic radiation. Photons are produced by a machine known as a linear accelerator, which is called a LINAC for short. A linear accelerator takes electrons and accelerates them to a tungsten target, which is located in the head of the machine. And you can see the head of the linear accelerator when you're in a treatment room. So the tungsten target is a high Z material, meaning it has a high atomic number. And so when electrons reach that high Z nucleus, they undergo what is known as a Bremsstrahlung interaction, also known as braking radiation. The electrons basically curve around that heavy nucleus, and that change in energy results in photon emission, or in other words, X-ray production. The electrons lose energy as they bend around that high Z nucleus, and they lose some energy, resulting in photon emission. So that photon that is produced, also known as an X-ray, the efficiency of that X-ray production is pretty low. So it's only around 33%, meaning the energy of the X-rays that is produced is only around 1/3 of the energy of the incoming electrons. Now, the photon that is produced, the reason we know that it is an X-ray as opposed to a gamma ray is because X-rays are produced extranuclearly. So the Bremsstrahlung reaction describes kind of how X-rays are produced extranuclearly. Gamma rays, on the other hand, are produced intranuclearly by the decay of a nucleus, such as a cobalt-60 nucleus. So in a linear accelerator, we are producing a specific type of photons called an X-ray. Once that photon is produced from the linear accelerator, we can use the linear accelerator to deliver radiation to patients. And when these photons leave the linear accelerator and they actually interact with our tissue, there are different interactions that can take place between the photon and the atoms within our tissue. So there are 4 main types of photon-matter interactions to be aware of. 3 of these are interactions that take place between the photon and the electrons that are in the orbitals of our atoms. And 1 of the interactions is between the photon and the nucleus. The probability of these interactions happening depends on 2 things. So number 1, the energy of the beam itself, and number 2, the properties of the tissue with which the photon is interacting. So any of these 4 interactions could theoretically take place at any given energy with any given material. However, the probability is going to be very, very different, and we are really interested in the probability of certain interactions happening. The interaction that predominates at energies used in therapeutic radiation is a photon-electron interaction known as Compton scattering. So basically, in Compton scattering, what happens is a photon will ionize an atom by transferring some of its energy to an outer shell electron, and that electron gets displaced, and that electron can go on to cause DNA damage. And the photon that gets scattered can go on to interact with more electrons and release more electrons that then can go and damage DNA. And the probability of that interaction, Compton scattering, happening is proportional to the electron density of the material. And it turns out that hydrogen actually has the highest electron density. So most of our tissue is made up of water, and everything else, like all other materials, including the calcium that makes up our bones and things like that, they all have a very similar electron density that's a little bit lower than that of hydrogen. And so the probability of Compton scattering happening within our bodies is pretty similar across the different types of tissue that make up our body. And Compton scattering is the most important photon matter interaction to be aware of at therapeutic energy levels. The other types of interactions listed here I go into more detail about in the video called Introduction to Radiation Physics, but coherent scattering and photoelectric effect are two types of photon-electron interactions. Coherent scattering is really not clinically relevant. Photoelectric effect predominates at energies used in diagnostic radiology, and unlike the Compton scattering, which is really dependent on electron density, photoelectric effect depends heavily on the Z, or the atomic number of the material. And the probability is proportional to Z cubed over E cubed. And so since that probability is so dependent on the Z of the material, there's a stark difference between higher Z materials, such as the calcium in our bones, versus the lower Z materials, such as the remaining soft tissue in our body. And so that explains the high contrast that we see on diagnostic x-rays between the bone and the remainder of the soft tissue. Pair production is a photon nucleus interaction that actually results in the creation of an electron-positron pair. And this interaction is relevant at much higher energy levels. So it becomes relevant at energies above usually 10 MV. But its probability also depends on the Z of the material. So let's get into more details about what happens when photons enter our bodies at therapeutic energy levels. As we just said, Compton scattering is the interaction that prevails at therapeutic energy levels. It typically prevails at energies between 25 kiloelectron volts to 25 mega electron volts. And the energies that we use in radiation therapy are typically on the order of 6 to 20 MV. And so that's why Compton scattering prevails there. An incident photon, so the X-ray that we generated from the linear accelerator, will enter the patient's tissue and interact with an outer shell electron. It has a high enough energy to actually displace that outer shell electron and cause it to be ejected from its orbital. That ejected electron can go on to either directly or indirectly cause DNA damage, and the scattered photon will typically have a lower energy than before it hit the electron. It hits the electron, loses some energy, and then gets scattered. And that scattered lower energy photon can go on to interact with more electrons and cause those to be released from their orbitals. A concept that is very commonly tested is this concept of the Compton scattering angle, or in other words, how much energy is retained within the incident photon after it gets scattered. And as you can imagine, as the energy of that incident photon increases, the direction of its scatter is more forward peaked, right? Because it's going to lose a certain amount of energy depending on the outer shell electron. And if it has more energy in the photon to begin with, it's going to have more energy to stay more forward peaked. So that's a long-winded way of saying that as the photon energy increases, the direction of its scatter is more forward peaked. So one potential thing that can happen is that there is 0-degree scatter, meaning the photon is coming in at a certain angle. It hits the electron, but it keeps going at that same angle. So the photon loses no energy. Another thing that can happen is that the photon gets scattered at 90 degrees. So it's coming at a certain angle, it hits the electron, and it gets scattered at 90 degrees. In that situation, the photon retains up to 0.511 MeV. And that number is very important because 0.511 MeV happens to be the rest mass of an electron. So if the photon is scattered at 90 degrees, it retains 0.511 MeV. And pay attention to the units because 0.511 MeV is the same as 0.511 MeV is the same as 511 keV. So 511 kilovolts or 0.511 mega electron volts. So those are important units to kind of pay attention to. But if the photon gets scattered at 90 degrees, it retains up to 0.511 MeV. If the photon is backscattered, so if there's 180-degree backscatter, meaning the photon completely flips direction, it retains half of that rest mass of an electron. So it retains up to 0.255 MeV or 255 keV. So I would just memorize these. 0 degrees, it loses no energy. If it's scattered 90 degrees, the photon is 0.511 MeV. And if it's 180-degree backscatter, it's 0.255 MeV retained within the photon. I would also pay very close attention to that unit. So remember that it's 0.511 MeV and 0.255 MeV. And just remember that one unit. And then if they try to trip you up with using kilo electron volts or something like that, you know that it's 0.511 MeV, and then you can convert as needed. So when we're treating with radiation, we're shining a beam of X-rays on the patient. A bunch of photons are entering the tissue, and they are releasing electrons via Compton scattering. And as they release more and more electrons from their orbitals, the photons themselves are also getting scattered, and they'll continue to, release more electrons as long as they have enough energy. And then as they lose their energy, that process is called attenuation. Now, the electrons that are released will have direct or indirect action to actually damage the DNA. So the direct effect is if an electron is released from that orbital, and it can go and directly interact with the DNA and cause damage. The indirect effect is if the electron leaves the orbital and it goes and interacts with a molecule such as water and then creates a free radical such as the hydroxyl free radical, and then that hydroxyl free radical actually goes and damages the DNA. So that is an indirect effect. Most of the damage that's done by the electrons is through indirect effect. It accounts for almost 2/3 of photon effects for DNA damage. The direct effect is then responsible for only 1/3. So indirect effect is more common, but this is what's happening then. This is the actual mechanism of DNA damage from photon radiation, and it relates to the electrons and how they directly or indirectly go and damage the DNA. So that's sort of what's happening at the atomic and subatomic level. Let's zoom out a little bit and think about what actually happens in the tissue as the photons are entering the body. So this diagram is a little bit funny looking that I made, but imagine a beam of radiation, so that triangle on the left-hand side, and photons are shooting out of that beam, and they are entering the tissue, and the circles are a bunch of atoms with that orange outer shell electron waiting to be released from the orbital. So a bunch of photons are coming at the body, which is just composed of a bunch of atoms that are all perfectly lined up here in this image. Initially, the photons will, go and interact with some of those electrons in that first row of atoms, and those electrons will be released from that orbital. And then, more and more photons will start to penetrate through and start to release more electrons from those orbitals. So what we find is that initially only one electron is released from that orbital in that first row. And then as we go a little bit deeper in, we get two electrons that are released from the orbital. And then as more and more photons start to get scattered, and also those incoming photons start to penetrate all the way through. By the last two rows, we see that consistently 3 electrons are released from their orbitals each time. So there's sort of a buildup that happens where in the first row, only 1 electron is available. Then as we go deeper into the tissue, 2 electrons become available. And as we go even deeper in the tissue, we start to hit a plateau where only 3 electrons are available each time. And obviously, this is a very simplified way of understanding this. This is happening on the orders of probably millions and millions of electrons, not just 1, 2, and 3 electrons. But I think you get the point that initially when photons enter the body, a few electrons are released. But it takes a little bit of depth within the tissue for us to get to an equilibrium where the number of incident photons as well as the scattered photons are resulting in an equal number of electrons released from their orbitals. So as we think about what is actually happening in the tissue inside of the body, there's 2 important terms that we need to define. So the first of those is what is known as Kerma, or kinetic energy released per mass unit. This value of Kerma refers to the energy that's transferred from a photon or an uncharged particle to the electron or the charged particle that actually causes the DNA damage. And in that buildup region, the Kerma is very high because there's a lot of kind of pent up energy waiting to be transferred from the photon to the electron. Another word for that is kind of the potential energy. So the photon has a lot of energy to transfer to the electrons. So that is what the Kerma refers to. The other term that we need to define is dose, which is what the body experiences, right? That is the amount of ionizing radiation energy that's actually absorbed by a substance. And that refers to the energy deposited per unit mass. So in radiation, we measure the dose that we prescribe in a unit known as gray. And 1 gray is a joule per kilogram. So it's the energy deposited per unit mass. So there's a difference between the Kerma, which is sort of the potential energy that's from those incoming photons, versus the dose, which is the energy that's deposited per unit mass. So as we talked about, the photon energy is what we call the Kerma, so the potential energy that's left for all of the photons beams to give. And that potential energy is the highest before it hits the body. And as the photons hit the body and start to interact with the atoms, they start to get scattered and they start to lose that energy. And so the Kerma is, highest at the beginning and it slowly drops. The dose, on the other hand, is what the body sees. And the body is really seeing the radiation in the form of electrons, right? Because electrons are kind of, in the end, what are actually going to cause damage to the DNA, either directly or indirectly. So the electrons are important for the energy that's deposited per unit mass. So the dose is not high until the electrons have kind of built up to that area of equilibrium. So Kerma is high in the beginning and it steadily drops as we go deeper and deeper into the tissue. Dose, on the other hand, is dependent on how many electrons are available, and the dose is at its maximum. So the Dmax that we see, or the maximum dose in the tissue, happens at a certain depth after we have achieved that electronic equilibrium that we talked about. And then, as the electrons start to interact with the DNA or interact with water and start to cause the damage, and as the photons continue to travel through the body and get scattered and lose energy, the dose and the Kerma both start to kind of linearly drop off as we go deeper and deeper into the tissue. But what's really, really important to realize is that there's a buildup region where the dose is lower than the Kerma. And once we reach electronic equilibrium in the tissue, then the dose is greater than the Kerma. And so I think now it makes sense to pause for a second and define two additional terms that are very important to understand for understanding photon beams. So these are attenuation and beam hardening. Attenuation refers to the phenomenon where X-rays are absorbed as they pass through tissue, and as we talked about, they bounce off of electrons, cause the electrons to get ionized, and each time they get scattered, and each time they're scattered, they lose some energy. So by hitting a sequential number of electrons each time, those X-rays are going to lose energy, and that process of how they lose energy is called attenuation. So the tissue itself attenuates the photon beam as the photon or the X-ray beam passes through. That process is known as attenuation. There's another phenomenon known as beam hardening, which refers specifically to polyenergetic X-ray beams. So if you think about a monoenergetic X-ray beam, that is a beam where all of the X-rays coming out of that beam are the same exact energy. Theoretically, they are all going to attenuate very similarly as they traverse through the tissue. With a polyenergetic beam, on the other hand, the lower energy photons are going to be attenuated faster because they are going to lose their energy faster and approach zero energy faster, theoretically. So lower energy photon beams will get attenuated more quickly. The higher energy photon beams in that polyenergetic beam, however, will tend to attenuate more slowly. And so as you go deeper and deeper into the tissue, that will then raise the average energy of the beam for a polyenergetic beam. And that phenomenon is known as beam hardening. So when we say the beam is hardened, that basically means it was a polyenergetic beam, and now the lower energy photons have preferentially attenuated off faster just by virtue of having lower energy. And so now the photons that are left to travel through the tissue have a higher average energy. So that beam is said to be hardened. And the way that we can kind of measure this is a concept known as a half-value layer, or in other words, thickness of a material that will half the intensity of the radiation beam. There's an HVL1, which is kind of taking that first half, so from 100% to 50%. And there's HVL2, which is taking it from 50% down to 25%. And you can go on and on and on by dividing by 2 each time. So for a monoenergetic beam where all of the photons have the same exact energy within the same beam, for a monoenergetic beam, the HVL1 is going to be the same as the HVL2. For a polyenergetic beam, however, once you have halved the intensity of the radiation beam, the lower energy photons, like we said, are going to be attenuated faster. And so the photons which are left are going to have a higher average energy, thus raising the average energy of the beam. So beam hardening is going to have occurred. And therefore, the HVL2, so the thickness required to take the intensity of the beam from 50% down to 25%, is actually going to be greater than the thickness required to go from 100% to 50%. And that HVL2 is greater than HVL1 for a polyenergetic beam due to this phenomenon of beam hardening. And there's a formula for calculating the HVL that we all have to memorize for boards. It's the ln of 2, which is also 0.693. So ln of 2 over mu, where mu is the linear attenuation coefficient of the material that we're using. So these are concepts of attenuation and beam hardening, and they're just important to understand kind of what these definitions mean and what these terms represent. I think those terms are a little bit complex to fully wrap your mind around, so it's okay if at this particular moment it's not fully sinking in. Let's back up for a minute though and think about what we talked about in terms of what the dose looks like and what that percent depth dose curve looks like as a beam is entering a patient. Remember, we showed that curve of Kerma versus dose, and I'll just stick it in here in case we forgot. But essentially, because we need electronic equilibrium, so kind of the same number of electrons available at all times to cause DNA damage, because we need an electronic equilibrium to reach that depth of maximum dose, there's first a buildup region where the dose, or in other words, the absorbed energy by the tissue that we're thinking about, that dose is not quite at its maximum until we reach electronic equilibrium. And once we do, that dose is equivalent to the Kerma. And then after we have finally achieved equilibrium, in the range of equilibrium, which is kind of the latter half of that entire curve after Dmax, where sort of a constant numbers of electrons are available, the dose actually exceeds the Kerma, because now electrons are constantly available, but the photons are being attenuated. So what that curve looks like, there's a buildup region, and then we hit a depth of maximum dose where the dose is at its maximum. And then because of attenuation, the dose starts to slowly fall off, almost linearly. That curve of that red curve showing the dose is what we see when we shine a beam inside the body. So now going back to this example picture of a single postero-anterior field shined on a vertebral body, what we see here is a cross section, an axial slice of a CT scan. We're at the level of a thoracic vertebral body, and we know that because we can see sort of the heart and the sternum anterior to the vertebral body. And we see this color schematic kind of drawn over the black and white CT scan. And that color has different shades of blue, green, yellow, and red. And the blue represents the 50% isodose line, so that's kind of what is receiving half of the prescription dose. And the red actually represents more than the prescription dose, so like 110%. So as we look at this PA field, we see that closest to the skin, so most posterior in the CT scan at the bottom of this picture where the beam is entering the patient's body, it's actually blue there, and then it slowly becomes hotter and hotter, so the dose increases. It goes from blue to green to yellow, and then finally to red. So that's our depth of maximum dose. And then from there, the dose starts to fall off again, and it kind of goes in reverse color, so yellow to green to blue, and the dose is decreasing again. So you can almost imagine that percent depth dose curve that we just plotted out on a graph. You can see that kind of playing out on the central axis of this dose cloud of an example beam that is shining through the patient. And that hot spot, we call it a hot spot, the area of greatest dose. That's what we see here in red. That hot spot is not at the skin. It's a little bit deep into the patient's body. It's at a certain depth within the tissue. And then slowly the beam will kind of drop off. Two important things to realize. Number one, if we shined a similar beam in the opposite direction, so in the anterior-posterior direction, we would similarly see another hot spot on the opposite side. So now on the anterior side, closer to the sternum and the heart in this picture. The other important thing to realize is that the depth of the Dmax, so the depth at which we hit that maximum dose, it's going to vary with the energy of our photon beam. So here are some percent depth dose curves, or PDD curves, for photon beams of different energies that might be used in therapeutic radiation. So one thing to keep in mind is on the previous photo, we kind of saw an axial slice, a segment of an axial slice of a CT scan, and we saw a dose cloud, so kind of representing in an axial slice what the dose cloud looks like. And what the percent depth dose curve that we plot really refers to what is happening along the central axis of the beam. So we're going to talk about it in the latter half of this lecture, but the energy is not completely uniform across the horizontal profile of the beam. But let's not focus on that for now. For now, let's just focus on what is happening as we go deeper and deeper and deeper into the patient, so along the central axis of the beam. So these are PDD curves for different photon beams of different energies that might be used in therapeutic radiation. So we have 4 MV, 6 MV, 10 MV, and 20 MV. And there's two important things that we see on this curve. So number one is the surface dose. And interestingly, the surface dose is actually higher at lower photon energies. So if you look at the very early part of this graph, so on the x-axis, we're looking at 0 millimeters depth. 0 millimeters depth is the surface dose on the patient. And if you look at these curves, the 4MV curve is the topmost curve here, is the topmost point. So the surface dose is actually higher for the lower photon energies. And so it makes sense then that higher photon energies would have less of a surface dose. The other important point to keep in mind is the depth of Dmax. So the depth of 100% dose for each of these curves is different depending on the energy. And the depth at which we reach that 100% dose is the deepest for the higher energy curve. So the depth of Dmax for 4MV is going to be shallower than the depth of Dmax for 20MV. And these are really, really important things to kind of understand. So the maximum dose is more shallow for lower energies, and therefore it also makes sense that the surface dose is higher for lower energies. For higher energies, so 20 MV now, the depth of Dmax is greater, it's deeper into the patient, and therefore the surface dose is also lower. So that is a really, really important concept to understand about photon beams of different energies. A quick little rule of thumb to calculate the depth of Dmax is that for energies that are 10 MV or less, we can just divide the energy by 4. So for 6 MV photons, 6 over 4 is 1.5, so 1.5 centimeters is the depth of Dmax. For a 10 MV photon, 10 over 4 is 2.5, so the depth of Dmax is 2.5 centimeters. Above 15 MV, we can divide the energy by 5. So for 15 MV photons, the depth of Dmax is approximately 3 centimeters. And for 18 MV photons, 18 over 5 is 3.5. So depth of Dmax is approximately 3.5 centimeters. So for energies 10 MV or less, we divide the energy by 4 to determine depth of Dmax. For energies 15 MV or greater, we divide the energy by 5 to determine depth of Dmax. And that's just a really quick rule of thumb that gives us an approximate number. For cobalt-60 machines, so gamma rays now, the 6, 10, and 15, 18 MV photons, we're talking about X-rays. The cobalt-60 gives off gamma rays. The depth of Dmax for that is 0.5 centimeters. And I just remember it has an even lower energy than 6 MV photons, and so it's 0.5 centimeters. But then I remember that quick rule of thumb. So up to 10, divide by 4, 15 or more, divide by 5. That quick rule of thumb to determine the depth of Dmax. And just to reiterate here, the biggest takeaways that we should understand about photon beams is that the surface dose is higher as the photon beam energy gets lower. So the highest surface dose is going to be from lower energy photon beams. The depth of Dmax is going to be higher for higher energy photon beams. So as the photon beam energy increases, the depth of Dmax gets higher, so it's a deeper depth of Dmax, and the surface dose gets lower. As the photon beam energy decreases, the depth of Dmax gets shallower, and the surface dose increases. Clinically, it's really important for us to realize that even photons of low energies that have a higher surface dose, that dose that is seen by the surface is somewhere on the order of 40 to 70% of the depth that we see at the Dmax, which is 100% dose. So we're not delivering nearly as much dose to the surface. A lot of times this can be a good thing because if we're aiming for a deeper target, then we know that our dose to the surface is going to be lower. So that actually helps decrease the dose to the skin and it helps decrease skin toxicity. However, if we want to include the skin in our target, so for example, if you are treating a sarcoma, for example, and it has invasion of the skin and it's actually involving the skin, and we want to treat something that's a deeper target, but at the same time, we want to make sure the skin is getting a high enough dose, we might consider applying a bolus, which is kind of a tissue equivalent material. And what that does is, if we imagine applying a bolus for the first, say, 1.5 centimeters for a 6 MV beam, that then, that bolus acts as the buildup region. And then by the time we hit the skin, we're already 1.5 centimeters in, which corresponds to the depth of Dmax for a 6 MV beam. And so by applying that tissue equivalent bolus, we can then kind of increase the dose to the skin and make sure that we're covering it properly. So that's something to think about when we're treating, with photons, but we also know that we want to include the skin in our target. We might need to apply bolus or a tissue equivalent material to kind of help act as that buildup region. And that way, by the time we get deep enough and get to the skin, we're at a more therapeutic dose and we're not at such a low dose. So deep breath, because that was a lot of material, and I do think that those PDD curves or those percent depth dose curves can be confusing. In that first half of the talk, we really focused on what is happening along the central axis of our beam. So kind of right in the central line where the beam is coming through the patient and kind of linearly going deeper and deeper and deeper into the patient. If you need to take a break now, I would think this is probably a good time to kind of pause, go back and rewind, listen from the beginning if you need to kind of recap everything we talked about. In the second half of this talk, we're really going to focus on the beam profile and the penumbra. So now we're no longer looking along the central axis and going deeper and deeper into the patient. We're actually looking on the horizontal axis as the beam is kind of horizontally encompassing a particular field area within the patient. So now the profile of the beam, not just what happens along the central axis. So as we think about the profile of a photon beam, imagine our ideal scenario, right? Say you draw a 10 by 10 centimeter field on the patient. Say you're treating the spine. We looked at a picture of a spine being treated earlier. And we've drawn a 10 by 10 centimeter field. Our ideal scenario is that outside of that field, there's going to be no dose, so no kind of horizontal spread of the dose. Inside of the field, as soon as we hit our target field, we're just going to have 100% dose all throughout that profile of the beam. So now we're looking at the beam kind of horizontally as it's entering the patient. So this is our ideal scenario, right? It looks like a box because we have 0 dose on either side of the field, and within the field, we go right up to 100%. Unfortunately, that is ideal scenario, but it's not reality. It is not the actual scenario. In actuality, just because of how the photons kind of also can kind of scatter laterally and how electrons can scatter, electrons that are created inside of our field can actually scatter laterally and contribute to kind of a lateral dose. The actual scenario ends up being that at our field line, we actually see 50% of the dose right at the edge of the field. In the central axis of the field, we build up to 100% dose, but then on the sides, we start to taper off, and then at the edge of the field, the dose that we see is actually 50%. And that's an important number to know, is that 50% is the dose that we see right at the edge of the field. That tapering of dose that we see near the edge of the field is known as a penumbra. And penumbra is really sort of a shadow. So imagine you're in a dark room and you shine a flashlight against the wall. If you look, the light is going to be brightest along the central axis of the flashlight, and then along the edges, it's going to get kind of fuzzy. And the fuzziness is going to change, and the area of that fuzziness is going to change depending on how close you are to the wall or how far away you are from the wall. So a penumbra is really kind of that fuzzy area that we see on the edges that's kind of lighter in color. It's not as bright as along the central axis. It's the same exact idea with the radiation. And the radiation dose at the exact edge of the field is going to be 50%. And we'll talk about different things that can kind of shape how that penumbra tapers off. Before we get into kind of penumbra and defining what that is and different types of penumbra, Let's talk a little bit about how we try to get an even beam profile. So we just saw that picture where at the edges of the field there's 50% dose, and then in the middle of the field the dose is much higher, it's at 100%. And so we get kind of what looks like a normal distribution curve in that horizontal axis. That's not always what we want. We don't always want the highest dose along the central part of the axis. Oftentimes we're treating larger areas and we want the dose to be evenly distributed across the entire kind of profile of the beam. So one way that we can achieve that is by inserting what is known as a flattening filter into the profile of the beam, or kind of like in the beam's path to alter the profile of the beam. So a flattening filter is a device that's actually placed in the way of the beam as it exits the patient, and it's a high Z material. And if you take a look at that picture, its shape kind of changes with the profile of the beam. So it has the lowest level of attenuation out at the sides where the dose is at 50%, and along the central axis it causes the highest level of attenuation to kind of even out that mountain that forms in the middle. So it ends up filtering out low energy photons most effectively, and the resulting beam that enters from a flattened beam then has a decreased intensity, but it does have a higher average energy just because the lower energy photons are effectively filtered out. So it has a higher energy and tends to have increased penetration. Sometimes in radiation therapy, we might use what is known as a flattening filter free beam. So typically in radiation therapy, the default is to have a flattened beam. So overall decreased intensity, but a higher average energy because we filtered out the low energy photons. Sometimes though, in special scenarios, we prefer to have a flattening filter free beam. We abbreviate that FFF. So if we have a 6 MV beam, but then we're using it with the flattening filter free, we call that 6X FFF beam, indicating that the flattening filter was removed. The flattening filter is removed and the beam profile then looks like what we saw on the previous slide, where it looks like a mountain. So the highest dose is in the middle and lower dose at the edges of the field. This is often used in stereotactic radiation treatments to increase the dose rate. It kind of increases the intensity of the beam and it creates more efficient treatments. The average energy of a flattening filter free beam is actually lower than a flattened beam, but the dose rate is increased because the beam overall has an increased intensity. So different ways that we can alter the profile of the beam. Normally we put in a flattening filter to kind of effectively filter out low energy photons and try to create a more conformal kind of even, something that looks even along that horizontal profile. That is normally what we use with a flattened beam. For a flattening filter free beam, we take out the filter. It looks more like that natural mountain. It has a lower average energy, but it's a much more efficient treatment, and it can be used for SRS treatments or stereotactic treatments to kind of increase the dose rate and deliver the treatment more efficiently or faster. Here is another image just to compare a flattening filter free versus a flattened beam. So the red line on the bottom is showing a flattened beam, a 10x beam that has been flattened. And then the blue line, so the line that's above, is showing a 10x FFF beam. And as we can see, the flattened beam has a more consistent profile across the entire beam, and that consistency results in a higher average energy. The flattening filter free beam has a much higher peak, but because of its lower lows, it actually results in a lower average energy. The effect of a flattening filter actually varies a little bit with depth. And at the shallowest depths, the off-axis dose, so the dose at the edges of the profile, can actually be higher than the central axis dose, creating a sort of horn-like effect. In the central axis, the dose is actually a little bit lower and it seems to taper in. So it almost looks like horns. And that's a pretty classic kind of profile for a flattened beam. As we get deeper and deeper into the tissue, however, that effect sort of wears off, and then the off-axis dose can actually kind of decrease a little bit just as we go deeper with the attenuation that happens. But at shallower depths, that off-axis dose is kind of accentuated, and so that's where we get that sort of horn-like appearance. So in terms of understanding a beam's profile and considerations around that, I think understanding what a flattening filter is and the utility of a flattening filter-free beam to deliver dose at a higher dose rate more efficiently, that's probably the most clinically relevant aspect of understanding a beam's profile. Penumbra, which we talked about briefly earlier, is also very important, but I think this is a concept that comes up more on physics boards than anything. So as we said earlier, penumbra is a region at the edge of the field where the dose changes rapidly. And it changes rapidly for a few reasons. So the transmission penumbra, the geometric penumbra, and the radiological penumbra. Well, great. What the heck are those? Let's kind of go through each of these one by one and understand the different factors that influence our penumbra, or in other words, how quickly the dose falls off the edge of the field. So let's start by talking about geometric penumbra. And I think for geometric penumbra, it's really easy to kind of understand this if we stick to our flashlight analogy. So when we think about how the radiation is reaching the patient, right, we have our source, which is in the head of our treatment machine. We have our patient who's laying on the table. And then we have our collimators, also known as our diaphragms, which are really the jaws and the MLCs that are helping to shape our beam in the way that we want it to. So our geometric penumbra is going to be affected by a few things. So number one, the size of the source. Number two, the source to surface distance. And number three, the source to collimator distance, also known as the source to diaphragm distance. They're the same thing. So if you want to think about it from the flashlight analogy, the source is the size of our flashlight. The patient is the wall, so our source to surface distance is the distance between our flashlight and our wall. And then our source to collimator distance, we can artificially create a collimator on our flashlight by just cupping our hands around the mouth of the flashlight, for lack of better words. So right where the light is coming out, if you cup your hands around it, imagine that's your collimator. So you can kind of create that source to collimator distance by thinking about what is the distance from the flashlight to the edge of your fingertips as you're cupping them around the flashlight. So hopefully that gives us a good perspective. And if you want to grab a flashlight and even try this out, I think that actually makes sense to understand this concept of geometric penumbra. As we just said, all of these things alter the geometric penumbra, and the first is the source size. So as the size of the source increases, the penumbra increases. And if you're standing in a dark room and you shine a pen light against the wall, and then if you're shining in the dark room and you shine one of those heavy-duty construction lights against the wall, the penumbra is going to be much higher for the heavy-duty light, or even a normal-size flashlight, compared to a tiny little pen light, right? So as the source size increases, the penumbra increases. We also said that as the source to surface distance increases, or SSD increases, the penumbra increases, and that makes sense. So if you are in a dark room and you shine a flashlight against the wall from 5 feet away, and then you take 10 steps back and now you're 15 feet away, the penumbra is going to be much larger. So you're going to see a larger fuzzy area on the wall when you're standing further away from the wall. So similarly, when we take the source and move it further away from the patient, it's going to be a wider penumbra of radiation. Finally, the source to diaphragm distance, or the SDD. This can also be called SCD, which is source to collimator distance. And remember, we said in our flashlight analogy, the collimators were the equivalent of cupping your hands around the flashlight. So if you're standing, let's say, 10 feet away from a wall, you shine a flashlight on the wall, the penumbra is going to be wide. And then if you take your hands and you cup it around the flashlight, you're going to kind of narrow down the penumbra that you see on the wall. So that's kind of the analogous to increasing the distance between your source and your collimators. As that source to collimator distance or the source to diaphragm distance increases, the penumbra is actually going to get narrower. It's going to decrease. So putting it all together then, we have our source size, our source to surface distance, and our source to diaphragm distance. And our source size and our source to surface distance are both going to, as those increase, that's going to increase our penumbra. On the other hand, as our source to diaphragm distance increases, our penumbra is going to get smaller. And so there's an equation for the geometric penumbra at a given depth d, and the equation is the source size s times the quantity of SSD plus the depth d minus SDD, all divided by SDD. And that equation's a little bit hard to memorize, but all I remember is that SDD is the only factor here that's sort of inversely related to the penumbra. So what are things that kind of are inverse relationships, right? Subtraction and division. That means as the SDD grows, the penumbra quantity is actually going to get smaller. So SDD is subtracted from the numerator, and then it's divided in the denominator as well. So that's sort of how I remembered this equation. But the geometric penumbra is SSD plus the depth minus SDD, all times the source size, divided by SDD. The other two types of penumbra, I think, are a little bit easier to understand than geometric penumbra. Geometric is probably the most complicated, and it has an equation associated with it. Transmission penumbra refers to attenuation that happens from the jaws or the MLCs themselves as the beam is passing through. So basically, at the lateral edge of the beam, as shown in this diagram, at both of the lateral edges of the beam, there's going to be more photons that are actually going to pass through the jaws or the MLCs versus on the inner edge of the beam. So on the inside of the beam, the photons are going straight through, but on the lateral sides, they're being sort of attenuated by the material that makes up the jaws or the MLCs. That constitutes transmission penumbra. So collimator jaws can sometimes be designed to match the divergence of the beam, but depending on what the field size we're using, we can still see some variance there. Multi-leaf collimators are actually designed to have rounded edges, and that helps to keep the transmission penumbra relatively constant across the range of leaf travel. So no matter where the leaf is in relation to the beam, it helps to keep the transmission penumbra somewhat constant. That is often tested. Why are MLCs rounded on the edges? And the answer is to keep the transmission penumbra relatively constant across the range of the leaf. The final contributor to our penumbra is the radiological penumbra, and this is created from electrons that are generated inside of our field that then scatter laterally and deposit dose on the outskirts of our field. So inside the field, remember in our percent depth dose curve, as we were going deeper and deeper into the tissue, we talked about an electronic equilibrium, because the number of electrons that are scattering forward essentially equals the number of electrons that are scattering backwards and the number that are scattering inwards, and then the electrons that are scattering outwards in all of those directions. So the electrons scattering outward equals the number of electrons scattering inward in that area of electronic equilibrium. And when we attain that electronic equilibrium, that is when our dose exceeds our Kerma along the central axis of the beam, right? Well, now on the edges of the beam, think about the electrons that are being created towards the edges and are getting kind of scattered out to the lateral edges of our field, but then there's no electrons to come back inside. And so this is an electronic lateral disequilibrium. And if we think about it, our radiological penumbra from all those electrons scattering laterally is just going to increase when our electrons are able to travel further. So what makes our electrons able to travel further? Well, number one, if we have a higher energy beam, the electrons will travel further. And number two, if we have a lower density material such as lung, the electrons will travel further. So the radiological penumbra is going to increase with higher energy beams and lower density material, such as lung. And the bottom line is that it results from electrons that are created within the field that then scatter laterally and deposit dose. These are like stray electrons. So this was a lot talking about sort of that horizontal profile of our beam. So here's a quick recap of everything that we discussed here. Our beam profile varies based on the distance from the center of the beam. And importantly, we need to know that at the edge of our field, the dose is going to be 50% of our prescription dose. Our flattening filters are going to influence our beam profile. So flattening filter-free beams have a higher dose rate, which makes them more efficient for delivering radiotherapy, especially stereotactic radiation, so the treatments can be faster because of that higher dose rate. But if we think about their average dose, it's actually a lower average dose. The reason for this is that when we do insert the flattening filter, it filters out low energy photons, and so it raises the average energy of the beam. So flattening filter-free beams have a higher dose rate, they're more efficient, but they have a lower average dose. And then finally, we talked about beam penumbra, or the fuzziness that we see on the edges of our field, that lower dose region. The beam penumbra is affected by several factors. So number one, our transmission penumbra, so the collimator jaw as well as the multi-leaf collimators. The geometric penumbra, and we talked about the source size, the source to surface distance, and the source to collimator distance in that flashlight analogy. And then finally, the radiological penumbra. So this is kind of those stray electrons that are scattering laterally. And we said that radiological penumbra increases with increased beam energy as well as lower tissue density. So that brings us to an end of everything I wanted to talk about in terms of photon beam properties. Now, I don't think I've presented every single thing you need to know about photons for the physics boards, but hopefully I've provided a big picture of what happens when photons enter our bodies at energies used in therapeutic radiation. And hopefully we kind of understand what happens along the central axis of the radiation beam, as well as that horizontal beam profile. And hopefully that kind of helps us to make sense of some of the things that we do when it comes to planning out our radiation fields, where those fields are going to enter the body, how we design our radiation treatments, when we apply bolus, and things that are actually relevant clinically. And then also kind of concepts that we need to understand for board exams, like the HVL values for polyenergetic beams. HVL2 is greater than HVL1 because of beam hardening. The penumbra and the formula for geometric penumbra and things like that that are really relevant for boards. I really think that it's much easier to understand the little details, especially in subjects like physics, when you actually understand the big picture. So hopefully I've done a decent job of providing kind of the big picture of properties of photon beams. And as I end here, I feel like I really need to reiterate, I am not an expert in physics. My only qualification is that I recently passed the physics boards, but it took me a really, really long time to understand some of these concepts. And so I wanted to really simplify it as much as I could, because that is how I learned, by simplifying things down to kind of the most basic layman's terms. So hopefully this helped, and I thank you so much for your time and attention.